so that's something to look out for. Now, to look at another one there, suppose we want to do minus 394. Now, if you're going to do that, you have to know how many bits you're working with. You can't just say, oh, well, it's always going to be this. Depends on how many bits you've got. So, if we work it in terms of 16 bits, well, let's see. Well, okay. Maybe I should have gone through hexadecimal. Hexadecimal's easy on this one. You just group them in groups of 4 bits and then look them up in that table. Leading zeros if you wish. So I've got 1, and then 1000 is 8, 1010 is A. Now you've got 4 bits per hexadecimal digit, so that's 12 bits. So to get 16 bits, I want that, minus. Now the usual scheme for doing that is this. You take your binary representation, and 1010. You change all the bits, and you add 1. And so you get F, E, 7, 6. Once you get this one, I did this one quickly last time, to get from here to here, you subtract all but the last one from 15. 15 minus 0 is 15. 15 minus 1 is 14. 15 minus 8 is 7. The last one you subtract from 16. Minus 8 is 6. So representation of negative numbers goes pretty quickly if you go through an intermediate representation of the absolute value, the positive version of the number. Boom, drops right out. Now, if you have any questions about this at this point? Okay, I'm going to show you now another algorithm that you probably have not seen. Well, let's shift to a different number. We have 27C, and we want to convert that into base 10. The usual approach to it is this, to say, well, that's 2 times 16 squared plus 7 times 16 plus, well, if you really want to write it all the way out, it's 12 times 16 to the 0. And so now you find the 16 squared, 2 times 256, and 7 times 16, and 12 times 1, and so we have here 512, 412, and 12, 636. All right. Here's an alternative way of doing it. Take your leftmost digit, multiply by the base, add the next digit, multiply by the base, add the next digit. When you get to the last digit, you're done. How does it work? Well, the way it works is this. If you look at this thing and factor out a 16, you're left with 2 times 16 plus 7 times 16 plus 12. That 16 to the 0 is just 1. You may have seen in programming, some of the fundamental programming stuff, some of the easy ways to evaluate a polynomial. See, if you've got 3x to the third plus 17x squared minus 9x plus 5. If you calculate all the powers and work them in, it's wasteful. You do 3x plus 17 times x minus 9 times x plus 5. It's a more efficient way of doing it. Doing exactly the same thing here. Exactly the same thing. And it becomes particularly useful. See, if you take a binary number like 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. See, the usual way of doing that is to say, well, let's see. We've got 0, we've got a 2. 2 squared is 4, 2 to the third is 8, 2 to the fourth, 5th, 2 to the 6th is 64, 2 to the 7th is 128, 2 to the 9th is 512, 10th is 1024, this is 2048. Now this is twice that, which is 4096, and 8192. And then this one is going to be 4 times that, 37, 32, and then add it up. It's a mess. You got so many terms in there to work with, and so many places you can make a mistake. Instead of doing that, well, I've done it in terms of hex. Let's do it in terms of 3 digits. Do it in base 8. In base 8, we have 1, 3, 5, 3, 1, 6. Base 8. Okay? Just, like I say, just right off of that table. So now to convert that, we take our first digit, multiply by the base, add the next digit. Okay, we got those two done. Multiply by the base, add the next digit. Multiply by the base, 4, add the next digit. Okay, let's see, we're at 747, multiply by the base, 56, 59, add the next digit. 5977. We're not done, so we multiply by the base. 8, 47. Add the next digit. 47,822. It's still kind of messy. You still got a lot of computation to do going through there, but particularly if you happen to be using a calculator, I mean, it's really easy. I mean, you just times 8 plus 3 times 8 plus 4, whatever, and you're in business. It goes a lot quicker. So those kinds of conversions back and forth, you use these heavily. Really makes it easier. Yeah?
So basically, like regardless of how long the number that we're converting, we're just taking the first number, multiplying times the base until we reach the end?
multiply the base, add the next digit, multiply the base, add the next digit, and when you add the last digit, you're done. Yeah. Nice algorithm, yeah.
On that, the black, the one with 27C, when you did, you multiplied by the base 16, and then you added 7, then you multiplied by the base 16 into 39, got 234.
That's not the right answer, is it?
Yeah,
No, you
Oh.
did- You
Where's-
did 16, then 8.
Yeah, that's right. It's 234, we got
where'd
partial
you-
products
yeah,
here.
where'd you get the 39? That's what I was just wondering.
1 times 39.
He's still multiplying.
Uh,
The final
Just
answer
the
is
standard
6.4.
algorithm for multiplying.
I see.
Never mind.
Yeah.
Okay,
This is just
Yeah.
intermediate step.
okay.
Hand back here,
Never mind, it was stupid.
okay?
You're just doing the multiplication.
Okay, well, there are a lot of other things that we can talk about here. You need to have some reasonable familiarity with these things, because as you work with the LC3 and you get that interface up there, it's going to show you what's in the registers and what's in memory and all the rest of that. And it's all going to be in, not decimal. Okay, so you need to be able to look at that and recognize what's going on and be able to work with it.
What are we gonna do with decimals and binary?
Fractional values,